Hi, I'm Nemanja Rakicevic, and I will be presenting our work titled Policy Manifold Search, Exploring the Manifold Hypothesis for Diversity-Based Neuroevolution, co-authored by Antoine, Cully, and Petar, Kormushev. Our work focuses on a typical reinforcement learning setting defined by a markov decision process, which consists of an agent acting in an environment from which it takes observations and decides which action to execute next based on the current policy. In standard reinforcement learning approaches, a single optimal policy pi is learned for a given environment task combination, and it is required to be robust to external factors such as disturbances, obstacles, as well as other agents. This works well in cases when the learned policy does not have to deviate too much in order to account for such factors and can still solve the task successfully. However, if certain disturbances or task variations are so great as if they were completely different tasks, this might fail. As well as if some cases which have been insufficiently seen during training occur, it can also lead to the learned policies breaking. Some examples include a robot with a damage to its leg, which is required to continue operation until the damage is replaced, or a robot which learns how to reach an object, and then during execution, previously unseen obstacles introduced, which leads the robot to have to find alternative ways to reach the object. In such situations, a single policy cannot adapt, and having a collection of different policies as backups would be a significantly better solution. Therefore, the goal of our work is to generate a collection of policies which lead to diverse behaviors. The main approaches in the literature addressing the issue of learning a collection of diverse policies include skill condition policies, which learn a single policy that is conditioned on the input by a skill indicator, which modify its behavior. And as an alternative paradigm is quality diversity approaches, which maintain a collection of multiple policies, and it consists of two main approaches, novelty search and local competition, as well as multidimensional archive of phenotypic elites, also known as map elites. And our approach takes inspiration from the latter. In the following slides, I will introduce the basic concepts and terminology required to understand our proposed approach. Then I will introduce the proposed policy manifold search approach, following by the experimental evaluations and results. In general, a policy can be defined as a function that maps observations to actions at each time step. Here we focus on a policy parameterized as a neural network, where the parameters are the weights and biases of the network. The policy takes as input the observations, which for example could be the robot and other objects' positions and velocities, and outputs desired control signals, for example the joint velocities or torques. In order to distinguish different policies, we need to define what is a behavior. So imagine we unroll the aforementioned policy parameterized by θi for t time steps. This gives us a sequence of t observation vectors for each time step, which we call a trajectory. For example, if we focus on the ball's position as an observation, we end up with the path of the ball. In order to quantify a behavior, we introduce a behavior descriptor, which maps the trajectory into a behavior index, which defines a location within our policy collection. In our example, we can focus on the path of the ball and take its final x-coordinate and maximum y-coordinate, which is a typical description of a ballistic trajectory, to define the behavior index. Then, to the cell, which is described by behavior index, we assign the parameters corresponding to this policy, which led to the trajectory. If we repeat this for n different policy parameterizations, we end up with n trajectories, which lead to n behavior indices. However, multiple different parameterizations can lead to the same behavior index, but we only have to keep one in order to maintain the diversity within the policy. Therefore, the goal of our approach is to generate and maintain such a policy collection. Let us now introduce the proposed algorithm. The first steps include generating randomly a set of initial policy parameters, which are then evaluated and possibly added to the policy collection. These two steps are typical for most of the quality diversity approaches. The following steps include using the existing policy collection in order to generate new policy parameters, which lead to new and diverse behaviors. These following steps can be implemented in a sample generation block. Here is an example of how this block is implemented in the map elites algorithm. The second step is to perform the parameter search, which includes sampling solutions from the policy collection and applying a mutation, which is typically a Gaussian noise, and then using the newly generated policy parameterization, which are then evaluated and possibly added to the collection. Inspired by map-elites, we propose the policy manifold search approach by hypothesizing that there exists a low-dimensional manifold embedded in the high-dimensional policy parameter space, around which a high density of solutions can be found. In order to validate our hypothesis, we perform manifold learning by training an autoencoder on all the policy parameters within the policy collection in order to obtain a latent representation space of the original policy parameter space. Subsequently, we can use the learned manifold in order to search for novel solutions. Similarly to map-elites, we search by sampling a solution from the policy collection and then projecting into the latent space using the learned encoder. And then from here, the naive approach would be to directly apply a mutation into the latent space and then reconstruct the samples. However, this leads to solutions which are not useful. Therefore, in our approach, after projecting into the latent space, we reconstruct the same point we projected in order to evaluate the reconstruction error. If this solution is represented well by the current autoencoder, its corresponding reconstruction error will be lower than the threshold value. In this case, using the encoded solution, we want to make sure that the corresponding novel solutions, once reconstructed to the original parameter space, will be distributed according to an isotropic Gaussian distribution. In order to achieve this, we need to calculate the Jacobian of the decoder and use this to determine the latent space covariance matrix, which is used to apply a mutation in the latent space by adding, for example, Gaussian noise in order to generate solutions which, once reconstructed back into the original parameter space, can be used as novel solutions to evaluate next. Alternatively, if the solution is not represented well by the autoencoder, we apply a standard map-elites search step by sampling a solution from the policy collection, applying a mutation in the original policy parameter space, and further using the generated samples. Therefore, this concludes the sample generation block of our proposed approach, which generates novel solutions, which are then evaluated in the environment and possibly added to the collection. This is an iterative approach which continues until the stopping criteria are met, for example, the maximum number of iterations. Next, I will present the environments used for experimental evaluations as well as the results. We introduced 4 continuous control simulated robot environments. First, Bipedal Walker is an OpenAI gym environment based on Box2D, with the goal of the bipedal robot to walk in many different ways. The action vector controls the 4 joint torques, while the observation consists of the robot's XY position, the leg joint position and velocities, as well as the LiDAR readings. The behavior descriptors is based on the final robot's XY position, as well as the leg ground contacts. The bipedal kicker extends the bipedal walker environment by adding a ball, and the goal is for the robot to kick the ball in many different ways to generate different trajectories. The action vector is the same, and the observation vector is augmented by the ball's position and the velocity. The behavior descriptor is based on the ballistic trajectory of the ball, as discussed earlier in the slides. Next, we also introduced a simple 2D striker, also based on Box2D, where we have the striker in red trying to hit the ball in blue in many different ways as possible. The action vector controls the striker's XY velocity as well as the angular velocity, and the observation vector consists of the striker and ball's position and velocities. The behavior descriptor is based on the final resting position of the ball as well as the walls it bounced off. Finally, we use the PyBullet-based Panda striker environment, which is similar to the 2D striker in the sense that it has to hit the balls in multiple different ways. However, the action vector controls all of the Panda's joint velocities, while the observation vector contains both the joint positions and the velocities, as well as the ball's position and the velocities. The behavior descriptor is identical to that of the 2D striker. In order to evaluate the performance of our proposed approach, we do an ablation study in order to evaluate our hypothesis regarding a latent space parameter search and to evaluate the contribution of using Jacobian scaling versus naive latent space search, and to evaluate the benefits of using a nonlinear versus a linear latent representation. Furthermore, we compared to several state-of-the-art methods, including elite hypervolumes, which perform search in a subset of the original parameter space, as well as data-driven encoding, which uses the autoencoder reconstruction error as a mutation operator. Both of these methods are quality diversity family of algorithms, and they use the notion of a manifold to perform the search process. We also consider diversity all you need as a skill conditioned policy approach. However, due to the long runtime, we didn't include it in this study. We also considered the original map elites as a baseline, as well as several random search approaches. To quantify the performance of each of the compared methods, we examined the behavior coverage. Behavior coverage indicates the total number of discovered behaviors during the training as a percentage of the cells filled within the policy collection. We plot the behavior coverage with respect to the total number of evaluations. Each column corresponds to one of the introduced environments, while on the bottom we have the legend. The highlighted methods are the three versions of our proposed approach, following by the state-of-the-art methods we compared to, and the baseline methods. In the first ablation study, we compare methods which use the latent space and the methods which use the original parameter space for the search process. We can group these methods based on whether they explicitly learn a policy manifold, like our proposed approach, or whether they use it implicitly, like in state-of-the-art approaches, or whether the search is performed directly in the original parameter space. As we can see in the graphs, using some concept of a manifold usually outperforms the direct parameter space search, while using an explicit definition of a manifold, like in our proposed approach, usually exceeds the performance of other methods or is on par with them. Next, we evaluate the contribution of Jacobian scaling by comparing our proposed approach with the version which does not take into account the additional transformation induced by the decoder. As you can see from the results, it is clear that not considering this additional transformation leads to a search which is similar to that of a random search. Finally, we compare nonlinear versus linear representation learning by examining two versions of our approach, one that uses an autoencoder for manifold learning and one that uses a PCA. As we can see in the graphs, using a nonlinear representation is especially useful in environments which have a nonlinear mapping from actions to observations, such as the bipedal environments. In addition to the behavior coverage plots, we also show the mixing ratios, which show the proportion of samples taken from the parameter space and from the latent space. At the beginning of the training, there are several salient peaks, which corresponds to more samples being taken from the parameter space, which is especially useful to improving the latent representations at the beginning of the training. And this can be regarded as a type of exploration within the search process. This is followed by several dips along the training, which correspond to more samples being taken from the latent space, and can also be regarded as a type of exploitation within the search process. Also, we can see that several of these dips correlate with jumps in the behavior coverage. To summarize our findings from the results, we can conclude that performing the policy search in the learned latent space leads to higher behavior coverage than directly searching in the original parameter space. Also, scaling the latent space sample covariance matrix using the Jacobian of the decoder is crucial. And finally, it is beneficial to use nonlinear representations for policy search, especially in certain environments. Thank you very much for your attention, and I will be looking forward to answering any further questions.